Hi friends, today we'll discuss about regular grammars. Three equivalent ways to describe exactly the class of regular languages are finite state machines, regular expressions, and regular grammars. Finite state machines and regular expressions I have explained in my previous video lectures. Today we'll be discussing on regular grammars, sometimes also known as right linear grammars. A regular grammar G is a quadruple V summation RS where V is a rule alphabet which contains non-terminals and terminals. Summation is a set of terminal symbols which is a subset of V. R rule set is a finite set of rules of the form x tends to y. S is the start symbol and is a non-terminal. In a regular grammar, all rules in R must have a left-hand side, a single non-terminal, a right-hand side, an epsilon, or a single terminal, or a single terminal followed by a single non-terminal. Some of the legal rules in the regular grammar are S tends to epsilon. Yes, LHS is a single non-terminal. RHS is an epsilon. S tends to A. LHS is a single non-terminal. RHS is a single terminal symbol. T tends to AS, where T LHS is a single non-terminal. RHS is a single terminal A followed by a single non-terminal S. So all these rules are legal and are in the format given, whereas S tends to AS. LHS is a single non-terminal, whereas RHS is having a terminal symbol followed by a non-terminal symbol. Again we have a terminal symbol. So such kind of rules cannot be written in regular grammars. Similarly, ASA tends to T. LHS must have only one single non-terminal, whereas here it is a combination of both terminals and non-terminals. The language generated by a grammar G is equals to V summation RS denoted by L of G is the set of all strings W in summation star such that it is possible to start with S, apply some finite set of rules in R and derive W. So to make writing the grammar easy, we will adopt the conventions that unless otherwise specified, the start symbol of any grammar G will be the symbol on the LHS of the first rule in the grammar. For example, consider a language over summation AB containing all possible strings of length even. Possible strings in this language are epsilon, string length 2 having AA, AB, BA, BB. Next string length 4 starting from AA to BB, BB and so on. So the possible regular expression for this language is AA or AB or BA or BB whole star or A union B, A union B whole star. How to write the regular expression? We have seen in the previous lectures. Then coming to the DFSM M that accepts L. So first string in the language is epsilon. So initial state will be the final state. Next, since the string length is even, so next is if string length is 1, A or B, then it must be in an intermediate state. So string length 1, it can be A or B, it is in intermediate state. Next, if it is 2, string length is 2, then it will reach the final state. Then string length 3 will be in intermediate state. Next string length 4 will be in the final state. So this is the DFSM obtained for the language with strings of even length. The regular grammar that defines L is, so initial state is S, and since initial state is the final state, then the first string is epsilon. So we'll be having first rule as S tends to epsilon. Next, from S for A, it is going to state T. So the next rule will be S tends to terminal symbol A and the state which it reaches, the non-terminal T. Similarly for B, S for B is going to state T. So the rule will be S tends to B T. Next, T tends similarly for T. T for A is going to state S. So T tends to AS. Similarly for B, T for B going to S. So T for B going to S. So this is the regular grammar written for this particular DFSM. So let us derive a string ABAB from the given grammar. So first S tends to, we'll go for applying second rule, S tends to AT. Here we got first A. Next from this T we must get B. So we go for using T as BS, last rule. So we'll have T as BS. So AB is over. Next we need a A. So we go for using the second rule, S tends to AT. So S is replaced by AT, and at last ABA is obtained. Last we need a B. So we replace T as BS, T as BS, and now the needed string is obtained. So finally we go for deriving S as epsilon. So the string derived from the start state S is ABAB. Regular languages and regular grammars. The class of languages that can be defined with regular grammars is exactly the regular languages. This can be shown by any language that can be defined with a regular grammar can be accepted by some FSM and so is regular. Then we must show that every regular language, that is every language that can be accepted by some FSM, can be defined with a regular grammar. So both the proofs are by construction. This algorithm constructs an FSM M from a regular grammar G is equals to V summation R S and assures that L of M is equals to L of G. So the first step in this grammar is to create M in M, a separate state for each non-terminals in V. Then the start state is the state corresponding to S. If there are any rules in R of the form x tends to W for some W belongs to summation, then create a new state labeled hash, which is the final state. For each rule of the form x tends to WY, add a transition from x to y labeled W. For each rule of the form x tends to W, add a transition from x to hash labeled W. For each rule of the form x tends to epsilon, mark state x as accepting. Finally, mark the state hash as accepting. Let us take an example for the language containing the strings over summation AB which end with 4 A's. Possible strings in this language are 4 A's compulsory. Before these 4 A's, you can have any combinations of A's and B's. So the regular expression for this particular language is A union B whole star representing any number of A's and B's before 4 A's. Coming to the regular grammar, the grammar is represented as, first we must write the grammar for arbitrary A or B. First, for A, S tends to A, S. So S is recursively calling itself to generate n number of A's. Similarly for B's, S tends to BS. So these two rules can take up any number of times representing any combinations of A's and B's. Next we must come across the first A. So first A is represented as S tends to first A followed by a new non-terminal or a state. Next to the next A, as it is a compulsory A, so from B for a A we will go to a new state C. This was for second A. Similarly for third A, from C for a A it will go to state D or a new non-terminal D. This was for third A, and finally for the last A it must reach the final state. So from D this will be the fourth and the last A to be generated. So this is the regular grammar for this language. So once we generate the regular grammar, apply grammar to FSM algorithm to this grammar to generate the FSM. So let us see how to generate step by step. So in the algorithm, first step is to create a machine with separate states for each non-terminals present in V. So here we have S, B, C, D, 4 non-terminals. So first step is to generate S, B, C, D, 4 states separately for 4 non-terminals. Second step is start state is the state corresponding to S. So the first rule non-terminal is S. So S is the start state. Third step, if there are any rules of the form X tends to W, where W belongs to summation, then create an additional state labeled hash. That is, if we have a non-terminal tends to a terminal symbol, is it there? Yes, D tends to A. Then what to do? Create a new state and label it with hash. Next, fourth step, for all the rules of the form, a non-terminal tends to terminal followed by non-terminal. So we have 5 rules here. So what to do? Add a transition of the terminal from X to Y labeled W. That is, S tends to AS. So from state S to state S, we must have a transition labeled A. So from S, self loop, transition A. Similarly from S, self loop to with label B. Self loop with label B. Next, from S to B, a transition labeled A. From S to B, a transition labeled A. From B to C, transition labeled A. From C to D, transition labeled A. So these were the 5 rules. Next, coming to the fifth step, for each rule of the form X tends to W, that is, a non-terminal tends to a terminal symbol. Then what to do? Add a transition from this non-terminal with a label A to the state hash D2 hash labeled A. Finally, do we have any transitions with epsilon? No. So go to the seventh step. Mark the state hash as the accepting state. So this is the FSM generated by applying grammar to FSM algorithm. Let's see the next example. The strings starting with ABB. Possible strings in this language are ABB followed by any combinations of A's and B's. The regular expression obtained is ABB followed by A union B whole star. Let's write the regular grammar for it. So first compulsory ABB string. So from the first variable S or the start state tends to first A goes to a new variable. Again from that variable A for a compulsory B it goes to next variable. Next from that variable B one more B goes to non-terminal C. So by now we have obtained ABB and we are in the variable C. From here we must have A union B whole star. So that is represented as C tends to AC, any number of A's or any number of B's in C going, or it can be epsilon. So this is the regular grammar. For this regular grammar, the FSM obtained is, so first step is for each non-terminal or a variable, we must create a new state. So here we have S, A, B and C, 4 states. Next, start state is S, so S is represented as start state. Next, if we have any rules of X tends to a terminal symbol, we don't have any terminal symbol, so hash state is not generated. In the fourth step, coming to S tends to AA, so we have 5 rules of that form. So that can be represented as S tends to A from state S to state A with label A. Then represent from A to B labeled B, B to C with label B, C to C with label A and C to C with label B. So we have self loop for C with label A comma B. Next, coming to the fifth step, for each rule of the form X tends to W, a single terminal symbol are not there in these rules. So we'll go for the next step, step 6. For each rule of the form X tends to epsilon, yes, we have for C tends to epsilon. Then what to do? Mark the state X as accepting. So here C is the state. So C will be marked as accepting state. And 7th and 8th rule will not be considered. So this is the final FSM obtained. And remember, these will not be deterministic, they will be non-deterministic FSMs generated from the given regular grammar. So this is the FSM obtained for this regular grammar. So let's see the next language containing strings which end with ABB. So possible strings in this language are ABB, and before this ABB you may have any combinations of A's and B's. So the regular expression obtained is A union B whole star ABB. So let's write the grammar for it. First we have A union B whole star, arbitrary number of A's and B's. For that we write the two rules, S tends to AS or S tends to BS. Then Coming to ABB compulsory string. So yes, we'll go for a new variable for first A. Then this A will go for another variable for the second symbol B, and at last B goes to B, which is the third symbol. So let's design the FSM for this particular grammar using the algorithm grammar to FSM. So in the first step, we are supposed to create the states for all the non-terminals. So here we have S, A, B, three non-terminals. So we have three states generated. In the second step, start state is yes. So we go for representing yes as the start state. Third step, if we have any rules where RHS is a terminal symbol, yes, we have B tends to B, then go for creating an additional state, label it as hash. In the fourth step, if we have the rules non-terminal tends to terminal followed by non-terminals. So we have four rules there. Then what to do? S tends to AS. So S will take a self loop for A. Similarly, S tends to BS. So it will take a self loop for A and B. Then S tends to AA. So S for A goes to A. Next, A for a B goes to B, and B for a B goes to hash. And at last, hash is the accepting state. So this is the finite state machine obtained for the given grammar. So the next language is containing a substring ABB. Possible strings are ABB. Before and after you can have any combinations of A's and B's. So the regular expression is ABB compulsory substring. Before and after we may have any combinations of A's and B's. So let's write the grammar for it. So first, any combinations of A's and B's will come across the same two rules. S tends to AS, S tends to BS. Then compulsory A, B, B string. And again, any combinations of A's and B's, and right now we are in variable C. C goes to AC or BC or epsilon. So this is the grammar obtained. The FSM for it will be, we have one SABC, four non-terminals. So we'll have four states SABC. Start state is yes. Then coming to the next rule. Third rule, we don't have any terminal at the RHS. Fourth rule, if we have non-terminal tends to terminal followed by non-terminal. So all these rules are of that form. At that time, for S tends to AS and S tends to BS, we have a self loop for A and B. Then from S to A for terminal symbol A, for A to B for a terminal symbol B, B to C for a terminal symbol B. Again we have C self loop for A and B. Then coming to the fifth step, again we don't have any single terminal at the RHS. Coming to sixth step, in the sixth step of the algorithm it states that if you have any epsilon transitions, then make that particular state as the LHS state as the accepting states. So we have here C tends to epsilon, so C will be the accepting state. So this completes the designing of FSM. So this is the FSM obtained from this regular grammar by applying grammar to FSM. So let's see a language of missing letter. Summation is ABC. The language missing is equals to having the string W where there is a symbol AI which belongs to summation not appearing in the string. That is, at a time one symbol of the alphabet will be missing in the string. For example, if A is missing, then we'll be having the strings of combinations of B's and C's. For example, CBBC, BBCC, etc. If B is missing, then we'll be having a combination of A and C strings, AC, CA, 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 etc. If C is missing, then combination of A's and B's strings, AB, AB, AABB, BBAB, etc. So let us design the grammar for this language. Initially, S tends to epsilon. Then if I have A missing, then I may have combination of B going to a new variable A or C going to a new variable A. Then in this variable I may have any combinations of B's and C's. So A tends to BA or A tends to CA, including epsilon. So A tends to epsilon. So these rules will be applicable for A missing. Similarly, if B missing, then S will go to B. S tends to AC or S tends to BC. So you can see here we don't have any rule for B. Next, from B, it may go for any combinations of A's and C's including epsilon. So B tends to AB or B tends to CB or B tends to epsilon. So B non-terminal is used to generate all the strings of A's and C's where B is missing. Next, similarly for C missing, we go for a new non-terminal C. S tends to AC or S tends to BC. Then any combinations of A's and B's, so C tends to AC or C tends to BC, C tends to epsilon. So here in C, we don't find any rule written for input symbol C. So A is a non-terminal which generates all possible strings excluding A in it, B excluding B in it, and C excluding C in it. And finally, the FSM obtained for this particular grammar is S tends to epsilon. S for a B or a C, it will go to S for a B or a C, it will go to A. A will take a self loop for B and C, and A tends to epsilon, so it is final state. Similarly, S tends to A or C goes to a new state B, and in B, B will take a self loop for A and C, and finally B tends to epsilon, so B is final state. Next, S tends to AC or BC, so S for A or B goes to C. In C, combinations of A's and B's including epsilon. So this is the FSM obtained for this particular grammar. So let us see one more language which satisfies multiple criteria. That is, the language contains the strings of odd number of A's and ends in a A. Then the FSM looks like odd number of A's. So initial state for one A reaches the final state T. If one more A, then it must return back to S. Third A, that is odd A reaches the final state. Even A comes to the intermediate state. Again odd A reaches the final state. Even A comes to the intermediate state. This is for odd number of A's. Summation is AB. So from S we have a transition for input symbol A. B can take a self loop as there is no criteria on number of B's at S. Coming to state T, T for A it is going to S. For B one or more number of B's, it will go to state X. Then coming to state X, it can take any number of B's, but for A, it must go back to the intermediate state S, wherein again we go for odd number of A's, and compulsory it ends with the A, not with the B. Then the grammar is S tends to BS, then S tends to first A, S T A T, where T tends to epsilon, where T is the final state, and from T for A it goes to S, and for B it goes to a new state X, where X for A will go to state S, whereas for any number of B's it will be in the loop. So let us derive a string BA A B A. So start with S derives BS, we got the first B. Then from S I need AA BA. So I'll go for S tends to AT. S derives AT. So I got BA. Next is T. From T I need ABA. From T will go for AS. So T is replaced by AS. Next from S I need BA. So I'll go for the first rule. S is replaced as BS. And finally from this S I need a A. I'll go for using AT. S is replaced as AT, where T at the last step by rule 3, T is replaced as epsilon. Hence BAA BA is derived from this particular FSM, from this grammar. So this is how we go for generating finite state machine from the given regular grammar. Thank you.